Welcome. In the last lecture, we discussed network functions. As we know, to synthesize a network, we need information regarding the input and output of the network. This information is available in terms of network functions. So having the network function for a network is the starting point in the process of synthesis. Suppose network immitance function Z of S is equal to NS divided by DS. If we have the information about the network immitance function of a network, does that mean we can synthesize a network using this network function? No. We first need to check whether the given network function is realizable or not. Realizable means whether this can be converted into a network or not. Let us first see the various forms of representation of a network function. We already know network function is the ratio of two polynomials in the S domain. So that means it can be represented as this form of network function is called the canonical or the general form. Canonical form of the general form of the network function or canonical form of network function. Here numerator and denominator polynomials are mentioned in S form where the highest degree of numerator is n and the lowest degree of numerator is 0, where the highest degree of denominator is m and lowest degree is 0. There is another form also, which is this form is called the factored form of network function. Network function because the numerator has been shown in factored form as well as the denominator is also shown in the factored form. This form is also known as the pole zero form of the network function. Let us see what are these z's and p's in this form. Here these z's, z1, z2 up to zn are called the zeros of the network function, zeros of network function, whereas these poles p1, p2 up to pn are called pm, are called poles of network function. We can find the values of these zeros by substituting the numerator factors equal to 0. Let us say substituting this s minus z1 to be equal to 0, s minus z1 equal to 0 will give s equal to z1, where this z1 is called the 0 of the given network function. Similarly, we can find s equal to z2 by substituting s minus z2 to be equal to 0 and so on up to s equal to zn. In the same way, if we substitute the factors of the denominator equal to 0, that is s minus p1 equal to 0, this will give s equal to p1, where this p1 is called the pole of the network function, and we can get the several poles by substituting all the factors equal to 0. That is, if I substitute s minus p2 equal to 0, I will get s equal to p2, where p2 is the another pole, and we can do so till the last factor in the denominator, and the last factor in the denominator is s minus pm, that is s equal to pm is the another last pole of the given network function. We can comment on the realizability of a network function by having the information regarding the zeros and poles of the network function, and these zeros and poles are to be plotted in a complex plane where zeros are represented by a small circle and poles are represented by a simple cross. Let us see some examples. Suppose this is the network function of a given network and we are asked to plot the poles and zeros of the network function, given network function. First, we need to find the poles and zeros of the network function. The zeros, as already stated, the zeros can be determined from the numerator and the poles can be determined by the from the denominator. If we substitute the numerator equal to 0, we get the values of zeros. Let us do so. S square plus 6s plus 8 equal to 0. The values of s after solving this equation will give us the zeros. I can factorize it into s plus 4 into s plus 2 equal to 0. This gives s equal to minus 4 and minus 2. That means s equal to minus 4 and minus 2 are the zeros of this network. Similarly, we can find out the poles of the network by equating the denominator equal to 0. Let us equate s plus 9 equal to 0. This gives s equal to minus 9. So that means at s equal to minus 9 we have a pole of the network, and s equal to minus 2 and minus 4 we have zeros of the network. Let us plot them. As we already know, S is a complex frequency term. That means it will have the real part as well as the imaginary part. So it can only be plotted on a complex plane. This complex plane is also termed as the S plane, where on the x-axis we have the real values and on the y-axis we have the imaginary values. We represent it by sigma and imaginary axis by j omega. Now over here, s is equal to minus 4 and minus 2. It means we have a 0 here at minus 2 and at minus 4. So to represent that a 0 exists over here, we need to circle these points. Circling these points refers to that there exist the zeros of the given network function. Similarly, at s equal to minus 9, let me extend it. Say it is minus 9 here. As at s equal to minus 9 we have a pole, so we will mark a cross here to represent that at s equal to minus 9 we have a pole existing here, and at s equal to minus 2 and minus 4 we have zeros here. This plot is called the pole zero plot. Pole zero plot of the network function. We can comment on the reliability of the network function by knowing the placements of poles and zeros on this plot. We will do it in further classes. Let us consider one more example. Suppose we have a network function z of s which is equal to s plus 2 square divided by s square plus 25. Here we again need to plot the poles and zeros of the network function. Again, the zeros can be calculated by substituting s plus 2 square equal to 0. Let us put s plus 2 square equal to 0. This gives s plus 2 times s plus 2 equal to 0. That is s equal to minus 2 and minus 2. This means this at s equal to minus 2 we have two zeros. Now equating denominator equal to 0 to find out the poles, s square plus 25 equal to 0. This means s plus 5j s minus 5j equal to 0. This gives s equal to plus 5j and minus 5j. This means we have two poles here which are existing at 5j and minus 5j. Let us plot them on the pole 0 diagram. Consider this as the S plane, where on the y-axis we have the imaginary part and on the x-axis we have the real part. Let us plot the zeros. These are zeros At s equal to -2, we have two zeros, so we will mark a circle at s equal to -2. And at s equal to plus 5j and minus 5j, 5j would be -2 -4, this will be minus 5j. So at s equal to minus 5j, we have a pole, as well as at s equal to plus 5j will be here, we have another pole. So this is the pole 0 diagram or pole 0 plot for this network function. Over here we can see at s equal to -2 there are two zeros existing, so we say that there is a multiplicity of zeros. Multiplicity of zeros, or there exist multiple zeros. The zeros where the points where the only single zeros are existing are called the simple zeros. These are called simple zeros and simple poles. Simple zeros. Likewise, this is a simple pole here. Simple pole, because at this point only one pole is existing. Similarly, this will be a simple pole. But over here we have multiple zeros. This is how we plot the pole 0 diagram or pole 0 plot for the given network functions. Let us consider one more example where z of s is given. Here again we need to plot the pole 0 diagram for the given network function. Let us first calculate the zeros by equating the numerator of the network function equal to 0. We have 2s equal to 0. This will give s equal to 0. That means at s equal to 0 we have a 0 existing of this network function. Now let us do the calculation for poles. For poles, we need to substitute the denominator equal to 0. As denominator has two factors, so we will consider them separately. S plus 2 equal to 0 and s square plus 2s plus 2 equal to 0. From here we can directly get that s is equal to -2 is a pole, and from here s square plus 2s plus 2 we need to factorize it. On solving this we get s these are the two factors for this quadratic equation. So I get s equal to -1 minus j as first pole and s equal to -1 plus j as the second pole. Now when we have all the poles and zeros, now we can start the plotting of these poles and zeros. Let us see. This s equal to 0, we have a 0 here. S equal to -2, we have a pole here. S equal to -1 minus j, we have another pole. S equal to -1 plus j, we have the another pole. So in total we have 3 poles and 1 0 for the given network function. Let us plot them. Let us consider this S plane and try to plot these poles and zeros over here. As at s equal to 0 we have a 0, so we will circle it like this, showing that we have a 0 existing here. At s equal to -2 we have a pole, so let me put a cross over here at s equal to -2. At s equal to -1 minus j, -1 minus j will be here. We have another pole existing here. At s equal to -1 plus j, -1 plus j, we have another pole existing here. So in total we have these 3 poles and the 0 for the given network function. This is how we plot the poles and zeros of the network function. In the coming lectures we will see how to realize how to check whether the given network function is realizable or not. Thank you.